What if a chemistry test graded exactly how you think, and not just your final answer? Welcome to this explainer. Today, we're looking at something that honestly completely turns traditional educational grading on its head. It's an incredibly dynamic simulation that really doesn't care if you stumble onto the right answer, just as long as you can catch your own reasoning in the act. Get ready, because what we're about to explore is absolutely fascinating. Okay, let's dive into this. We're looking at the trace. This is a simulation created by Patience Learning. Now, on the surface, it looks like a 15-day individual chemistry simulation, right? But beneath that surface, it is actually a brilliant disguise. It's an entire course in cognitive psychology hidden inside a gripping, high-stakes environmental investigation. So here is our roadmap for today. We'll start with the Millhaven water crisis, explore the investigation mechanics, and uncover the cognitive bias traps. Then, we'll reveal the hidden interaction mechanism, and finally, look at how this completely flips the paradigm of grading student thinking. Let's get right into it. Section 1. The Millhaven water crisis. The Trojan horse. In this simulation, students are cast as lead analysts investigating some really abnormal drinking water readings. The residents are scared, the town council is demanding answers, and the EPA, yeah, they want data immediately. The students have to navigate 4 completely different potential sources. You've got Site Alpha, an abandoned industrial chemical plant with heavy metals. Then there's Site Beta, an active agricultural farm leaching nutrients and E. coli. Downstream is Site Gamma, an aging municipal water treatment plant dealing with severe budget cuts. And finally, Site Delta, a natural limestone karst system with naturally occurring arsenic. They have to figure out where the real threat is actually coming from. Section 2. The investigation mechanics. Pressure, time, and money. Because, let's be real, an investigation without constraints is just a glorified worksheet. Every single choice in the trace carries immense weight. First up is the budget. Students start with exactly $7,000. That's it. Every single test they order, whether it's a cheap $50 field test or a massive $500 advanced laboratory analysis, costs money. If this budget hits zero, boom, the investigation ends immediately. There is absolutely no magical grant money coming to save you. Every dollar spent is a strategic choice about what information is actually worth having. Next up is the time constraint. Students have a strict 14-day limit to solve this crisis. And tests take time to process. An advanced test might literally take 2 to 3 days to return results. This limitation keeps the tension incredibly high, forcing students to plan ahead and manage their time just as carefully as their budget. Then we have the confidence score. Regulators require a minimum of 75% confidence before they will even lift a finger to act on a recommendation. You can't just guess. To hit that threshold, students must build a coherent evidence picture across multiple sites. They have to collect quality data, confirm unusual results with repeat testing, and establish broad baselines. And finally, the absolute masterstroke of the mechanics, the Community Risk Index. This number rises every single day that residents continue drinking water without a verified recommendation. This introduces a brilliant ethical tension. If a student acts way too fast on incomplete data, they risk a wrong recommendation. But waiting for perfect data? That just means more days of community exposure to contaminated water. It's a constant, heavy balancing act. Section 3. The cognitive bias trap, mapping the mind. And this brilliantly illustrates that it's not just a chemistry game, but a psychological obstacle course. The simulation purposefully triggers these targeted cognitive biases over the course of the 14 days. By letting students fall into these very natural human traps like selective attention, where they fixate on an industrial plant while totally ignoring alarming data from a farm, or the IKEA effect, where they overvalue their own data compared to independent lab data, the simulation teaches them how to navigate uncertainty. More importantly, it teaches them productive failure recovery, basically how to recognize a bias, admit a misstep, and pivot their strategy. Let's look at a really concrete example that happens on day 3. Automation bias. The student orders a test using a portable XRF instrument at the abandoned chemical plant. The instrument spits out a massive, terrifying reading of 128 parts per billion of chromium. The instrument even passes its own self-check. But here is the trap. It's actually suffering from matrix interference due to the specific water chemistry at that exact site. The true lab-grade result, which arrives a whole day later, is only 38 parts per billion. But by then, many students have completely trusted the machine, drained their budget, and committed to a false theory. It's a harsh, incredibly effective lesson in not blindly trusting automated data without understanding the context. Section 4, the hidden interaction mechanism, the day 10 calculated risk inflection point. So on day 10, a boil water advisory hits and children are hospitalized. Behind the scenes, here is the brilliant multi-source mechanism causing the crisis. Step 1, Holcomb Farms agricultural runoff adds heavy ammonia to the creek. Step 2, the aging treatment plant downstream tries to disinfect the water by adding chlorine. Step 3, that ammonia chemically reacts with the chlorine to form weak chloramines, which don't disinfect well at all. Step 4, the chlorine demand of the water hits 4.8 milligrams per liter, completely overwhelming the plant's maximum dose of 2.0. The result? Total disinfection failure. But here's the kicker. Students can only discover this if they cross-reference the plant's operational rainfall logs with the farm's nutrient data and order a hidden chlorine demand test. Nobody prompts them to do this. They literally have to connect the dots themselves. This reveals the multi-source truth of the simulation. Site alpha provides chronic heavy metals, site beta provides acute nutrients and bacteria, and site gamma amplifies the failure because of its aging infrastructure. Most students completely miss this compound disaster. They get severe tunnel vision on the spooky, abandoned chemical plant and miss the quiet, devastating interaction between the farm and the water treatment facility. Section 5, Grading Student Thinking. Flipping the assessment paradigm. How in the world do educators evaluate a 15-day emotional journey like this without grading the final answer? So the crucial point is that we are looking at archetypes of reasoning, not just final answers. Consider the signal reader. This student builds a methodical foundation, notices correlations across different data sets, proves the interaction mechanism, and achieves a massive confidence score. Contrast that with the tunnel visionary who goes super deep on one site, completely ignores contradictory data from elsewhere, and ends up stuck with a really low confidence score. The assessment here is purely diagnostic of the reasoning processes and how they adapt to new information. The grading system itself is incredibly lightweight, just 36 points total. 16 points come from a daily journal, where students are assessed holistically on the quality of their reasoning, how they interpret evidence, and their real-time awareness of their own biases. The remaining 20 points come from a final reflection, focusing on specificity and honest self-assessment. The entire grade rests on their signature capacity, thinking about your thinking, also known as metacognition. It's all about catching their biases in the act. I actually want to read this quote directly from the teacher guide because it is just so powerful. A student who pursues the wrong theory but demonstrates clear reasoning, honest self-assessment, and thoughtful course correction will score higher than a student who stumbles onto the right answer without understanding why. This philosophy completely and beautifully redefines what success looks like in a science classroom. It prizes intellectual honesty over lucky guesses. Which leaves us with this final provocative thought. As we look at the landscape of education today, are we merely teaching students what to think, or are we actively giving them the tools to catch their own reasoning in the act? The trace proves that it is entirely possible to design an experience that does exactly the latter. I challenge all the educators listening to think about how you can bring this level of experiential, metacognitive learning into your own curriculum designs. Thanks for joining me on this explainer. Keep asking questions, and I'll see you next time.